math whizzes. Who is ready for some Monday math? I am. We love Monday math, don't we? Yay! And last Thursday, after we took our test, by the way, you guys did very, very well. I had three, the closest to 100% were three individuals, as I have stated, or depending where you are, will state in English class. But there are three individuals who almost had perfect papers, 2 away. That's pretty good. 23 out of 25. And so they did very well. And they set the curve for the math test. And those three individuals, sometimes we like to name names. I won't do A's, lots and lots of A's. Nothing was worse than a B. And so that's not too shabby on a new concept for you guys. But we had three people, and those three individuals are namely, and in no particular order, Caden, Anna, and Micaiah. All right, good job, guys. Really proud of you. Thanks for your hard work in that. I know, again, it was new concepts and not an easy test. And we certainly did not have the review that we usually do. You guys did very well. Remember to take good notes, because you get to use those on your test, as you now know, through the remainder of the year in our cyber schooling that we're doing. And so we started last Thursday a chapter number 11 on radicals. And we went through section 1 of that and how to express radicals to different degrees. Commonly it's square roots, can be cubed roots, and it can be in Espanol cuatro roots and higher than that. So we went through all of those, and we're going to move on today. We are in section 2 of chapter 11, in which we're going to be simplifying radicals. Simplifying radicals. I like this. This is some fun stuff. I think I mentioned to you maybe on Thursday, pre-algebra has already had this chapter. Now it's at a lower level than what your guys' is. And yours is quite a bit more challenging than what theirs is. However, they just went through a chapter on radicals, and it was tough for them, but they did it, and I'm proud of them, and I'm proud of you too, and you'll do okay as well. Now, as you'll see in black at the top, make sure in simplifying radicals that you get these two very important notes down, and especially this one, okay? The nth root of x times y is the same thing as the nth root of the square root of x times the nth root of the square root of y. And so what we're doing here is we can write them collectively, as long as they're being multiplied by each other, and in both cases they are. We can write them collectively, or we can break them apart and we can write them separately. Either way, we can do that, not a major deal. And so what we're going to do is consider in section 2 of chapter 11, when you don't have perfect roots, whether squares or cubes, there are things that you can still do to reduce them. I would like for you to get your calculators out. And just like with our pre-algebra class in this unit, I'm going to let you guys use your calculators on this, okay? Because they're going to be, as you can tell right down here, some super duper large, ridiculous, unfun, yet kind of cool too, numbers. And so I want you to have your calculators and for you to have a little bit of an advantage in that. Now for these simpler ones, we're not going to need them. And I'll tell you what I told pre-algebra, there are going to be a number of these. In fact, I believe it's all of them today that you are not going to be able to perfectly solve in proper form on a calculator. So while you can use a calculator to help you get to the right answer, you will not be able to use a calculator just to give you the right answer. Now, it technically may be correct, but it has to be written in standard form. And I don't believe any of you has a calculator that will do that for you. And so use the calculator to help you, but don't just completely depend on it, because it's not going to get you to where you want to be in your desired destination. Using the rule right up here, that if you have one number under, this is square root. Now down here, every now and then, notice we'll mix in today a cube, and we could have to the 4th, to the 5th. We're not doing those today. But keep an eye out for that number being different. Remember, if there's no number written in this V area, upper, there is right there. But in all these to which I'm pointing, that is assumed it's a square root. It's understood it's a square root. So we're dealing with a square root of 24. Well, 24 is not a perfect square. right? It would be wonderful. There's one away from being. 25 is a perfect square because the square root of 25 is 5, because 5 times 5 gets you to 25. But it's not a perfect square. However, an easy way of doing these, I like to do them. There's 2 ways of going about it, and I'll show you both of those, and then we'll probably do the easier way for the rest of it. But let me show you here. I'll show you kind of the longer way of doing it first, and then I'll show you the shortcut, and you pick which of the 2 you want. But I'm just going to use the shortcut from here on, and I think you'll probably like that one better too. All right, let's get all the prime factors of 24, okay? So let's break it down. And first of all, what are 2 common factors of 24? Let's just say 8 and 3. Is that okay with you? All right, we have the numbers 8 times 3, right? But we can break that down even further as far as prime factors go. We can break 8 into 4 and to 2 and keep our 3. Now I'm not doing the tree, I don't have room for it, but you understand what I'm doing. You're far enough along. 4 times 2 is 8, and 8 times 3 is 24. Just make sure 8 times 3 is 24. Make sure every step you're still at 24 when they're all multiplied together, and you're good. I just broke 8 down into 2 multiples, 4 and 2, and I retained my 3. Now I'm at 2 and 3. Those are both prime numbers, but what I need to do is I need to break down that 4 into a perfectly prime expression. And I can do that this way. 4 is 2 times 2. Then I retain this times 2, and I retain this times 3. Okay? So broken down into its multiples, here's what I have. The square root, because it's the square root of 24, not just 24, but the square root of 2 times 2 times 2 times 3. Okay, that's the same thing as the square root of 24, because when you multiply them all together, you still have 24. Now, what I can do, guys, is this. I can see how many of the same number do I have. Okay? And if I end up at 2 of the same number, when they're all broken down into prime form, prime factored form, if I have 2 of the same number, then I can just pull one of those 2 to the outside of the parentheses. And here's the reason why. What is 2 times 2? 2 times 2 is 4. What's the square root of 4? 2. And so I can pull out the square root of 4 to the outside, and just as a 2, no longer under a square root, because the square root of 2 times 2, or 4, is 2. Okay? And if you want, here's a way of looking at it. Whenever I just get 2 of a number under a square root, now if it's under a cube root, it has to be 3 of that number. Okay? But if I get 2 of the same number under a square root, I can just use one of those, cross them out, and pull out one of those to the outside. And so what I would have on the outside is 2, but notice what I still have under the square root. 2 times 3. And since I no longer have 2 of any prime number left, but just one of each of those, I multiply those back together. 2 times 3 is what? 6. And so my answer is 2 outside of the square root times, understood, 2 times the square root of 6. And that's my answer. Okay. Now listen, that's the long, complicated way of doing it. I don't like that way. Let me show you an easier, simpler way. I'm going to erase this, okay? If you need to, you can pause right now. Or if you want, you can rewind and write that down. I'm going to show you the easier way to do this, and from here on, that's the way we're going to do it. But that's the long mathematical process of doing it. I like shortcut mathematical process of doing things. Don't you? A lot easier. Okay. If I have the square root of 24, what I can do is I can break this down again into factors, okay? Which is what we just did. But here's what I'm going to do this time. I'm going to choose a perfect square root number so that when square rooted, I can just bring that out, and whatever's left over, just leave that underneath the square root symbol. Okay? What are 2 factors of 24, one of which is a perfect square? 3 and 8 wouldn't work because 3 is not, nor is 8 a perfect square. How about these 2? 4 and 6. Why did I choose 4 and 6? Because when multiplied they make 24. But also one of these, and that's the number 4, is a perfect square. Okay? So if I take the square root of 4, what do I have? Well, the square root of 4 is just the number 2. And so I can pull that outside of the square root of 4, pull that outside of the square root symbol, and leave it multiplied. Even though we don't have a dot, it's understood, right? Just like it kind of operates similar to a parentheses, a number outside of parentheses. Understood is multiplied to. What do I have left? 6. 2 square root of 6 is the simplified form of the square root of 24. I like that way better, don't you? That's a lot easier, guys, if you'll do that. And for these big numbers, you can still do that, but just use your calculator, okay, to pull it off. Now, for this one, we'll do that very thing. No, our calculator is too small of a number. We don't need to. But for 1b, what is the square root of 25? Well, 75. 75 is not a perfect square. And so I can't just take the square root of 75 and have an answer that has any whole number in it. But what I can do is ask myself, what are 2 factors of 75, one of which is a perfect square? And what I catch myself noticing right off the bat is, well, what about the number 25? Because I know 25 is a perfect square, and all I need is 3 25s, 25, 50, 75, 1, 2, 3, 3 of those. So 25 times 3, and 25 times 3 as the radicand, remember our terminology from Thursday? 25 times 3 as the factored radicand is the same thing as the square root of 75. And the reason I did that is because I know off the top of my head the square root of 25, and you do too. What times itself gets you to 25? And that's the number 5. And so I can take 5, which is the square root of 25, and just pull it outside of the square root symbol, understood that it's still being multiplied to that square root symbol as it was being multiplied under there. And with what am I left, guys, under the square root symbol? The number 3. And so the square root of 75 simplified is 5 square root of 3. And I did that by factoring, one of which I made sure was a perfect square. Now, similar to that, we can do that very thing on a cube, except we have to ask ourselves, what is a perfect cube that is a factor of the cube root of this number, 40? And so what number do I know that is a perfect cube? And remember, start small on cubes because they get exponentially larger than the exponent of 2, or a number squared. And so let's start at the most basic. How about 2? What is 2 cubed? Or 2 times itself twice. 2 times 2 times 2. Well, 2 times 2 is 4, and 4 times 2 is 8. So the cube of 2 is 8. Is 8 a factor of 40? Yes, cool. We're on the right track. And so I'm going to break down this one number, the cube root of 40, into the cube root of 2 factors of 40. And what times 8 gets me to 40? That is the number 5. And so the cube root of 40 is the same thing as the cube root of 8 times 5, because 8 times 5 is 40. But the reason I chose 8 is because I know it's a perfect cube. And so I can take the cube root of that one factor, 8, and I can pull it outside of the cube root value, and it's still being multiplied to the whole thing. But I have to ask myself, what is the cube root of 8? Or what times itself gets me to 8? And as we stated prior, that's the number 2. And so the cube root of 8 comes to the outside of the cube root value. And with what am I left then on the inside? Just the number 5. And so the cube root of 40 simplified is 2 cube root of 5, or 2 times the cube root of 5. Now again, if you punch that into your calculator, you're going to end up with a number that's a decimal. A number that's a decimal. A number that's a decimal. And that's no good, because that's not in standard form, even though that's technically correct. Guys, to get the right answer on these, you have to write them in standard form, because that's what's being asked, and your calculator is not going to tell you any of these things. You're going to have to be able to do this basic math, which is really nothing more than the working of that glorious multiplication table, like we did last chapter. Basically, it's just the multiplication table, factoring. We're doing radicals in the form of square roots, cube roots, and Espanol, cuatro roots, cinco roots, etc. It's really just multiplication table is all that it is. And I know it's a little bit beyond that, but not much more. So you guys can do this, and you can do very well in it. Now on this one, the square root, okay, the square root, I'm not going to use a perfect square. And the reason for that is I'm going to use as large of a number as I can just see, like that I know will go into 648, the square root of 648. Obviously 2 would work, but man, it's going to take forever if you go breaking it down in that way. So here's something I'm going to do. I'm going to put my phone over here somewhere. There you go. I think you can see it now. I'm going to put my phone, okay, so you can see this. I'm using my calculator. And what I'm going to do is I look at 648, and I notice 8 goes into 64. And 8 goes into 8. And I really don't need a calculator for this, so I'm not even going to do it right here. I'm just going to show you, and you can do that too. If I factor 648 into, I better write fairly small to make sure I keep myself with enough room. If I do 8, okay, 8 goes into 64 how many times? 8. Okay. 8 goes into 8 how many times? Once. So look at that. I can do it without a calculator. 648 broken down into 2 factors, one of which I know has to be 8, because 8 goes into 64 and 8 goes into 8, and I just figured out 81 times, okay? In other words, 8 times 81 is still 648. And so this is just as accurate as writing the square root of a number that way. And that works out really well for me, because look, even though the number I chose isn't a square root, or isn't a perfect square, 81 is. And here's why. What times itself gets me to the number 81? What times itself gets me to the number 81? That number, guys, is 9. And so I can take the square root of 81 and I can pull it to the outside of the square root symbol, because the square root of 81 is simply the number 9. And that with which I'm left is only the number 8. Look how much progress I've made almost in one step, I guess technically 2. Isn't that neat how quickly you can whittle that down? But here's the thing I need to ask myself. I'm not yet in prime form right here, and is there a perfect square that is a multiple of 8? And the answer to that is yes. And I'm going to rewrite my 9, but I'm going to rewrite that number 8 as 2 factors, one of which is a perfect square, and that perfect square is the number 4. And what times 4 gets me to 8? 2. And see, I've written the same thing, 9 square root of 8, but I've done so in factored form, one of which is a perfect square, and I've done that because I can pull the square roots of 4 out to where this 9 is. And so I'm going to do exactly that, but look at the sign. It's multiplication. And so what I have is this. 9 times, what's the square root of 4? What number times itself gets me to 4? The number 2. And so in pulling out the square root of 4, which is 2, I have to keep that multiplication action, for lack of a better way of putting it. 9 times 2 times the square root of, what number do I have left under that square root symbol? The number 2, and you can't simplify that any further. That's in prime form. But to have a final answer, I do have to multiply 9 times 2. What's 9 times 2? That is 18, but I keep times the square root of 2. And so my answer is 18 square root of 2, and taking the square root of 648. That's a little more complex, isn't it, than the baby math we were doing before. Well, we'll hang this tight because we got we got bigger fish to fry right down here. What's the 2b? What's the cubed root of 14,000? How about I put a comma to make it a little clearer? What's the cubed root of 14,580? Okay, now here's where I want to use my calculator, and I want to show you guys how to do this. Since it's the cubed root, and that is a huge Mongo number, what I want to do is try to whittle this down as quickly as I possibly can, and so I'm going to choose a large number. So we have 14,580 with which we're starting. Okay, I'm going to try to find a factor that I know is a perfect cube that's a sizable number if I take its square root. And for instance, what's the cube of the number 3? 3 times 3 times 3. Okay? 3 times 3 is 9. 9 times 3 is 27. And so I know the cubed root of 27 is 3, and that would be simple to simplify. And so I'm going to see if in this big cubed root number, 14,580, if what I know of a number, 27, to be the cubed root in the end to be 3, I'm going to see if 27 will go into 14,580. Hey, and looky there. It does. Okay, so my two factors are 27 and what else? 540. And so I'm going to write down these two numbers. Okay, I'm going to write down, it's the same thing as the cubed roots of 27, okay, and times 540. All right? Now, the reason I've done that, guys, is because I can pull out of there to the outside the cubed root of 27. Because I know what times itself equals 27, which is what? What's the cubed root of 27? That number is 3. And so I can pull out of there 3 to the outside of that cubed root symbol. See that here? And I'm sorry, I know I'm blocking it. I do that a lot, don't I? So the number 3 times the cubed root of what's left? 540. Okay. Well, listen. 3 times the cubed root of 540. Does that all make sense up to this point? 27 is working so well for me. I know the cubed root of 27 to be 3. And so I have 500. Let me clear all this off. I have an easier way to do it, but I don't want to make it look too confusing. I have 540 left, right? 27 worked well for me. And look, 54. How many times does 27 go into 54? We wouldn't need our calculators to do this, but I want to show you. 540 divided by 27 is what? The number 20. And so I can use, don't forget to write your 3 cubed root of, and I can use 27 a second time because it'll go into it again. That's a perfect cube. That's easy to pull that out from underneath the cubed root symbol to the outside. And what I have left over is the number 20. Okay, so what I'm going to do is I'm going to pull out the cubed root of 27 to the outside, keep the multiplication sign, okay? And so what I'm going to have is 3 times 3 cubed roots of 20. All right. And can anyone tell me, what is 3 times 3? Well, 3 times 3, I'm going to write over here. I'd write down here. Can you still see? Sorry, I know it gets scrunched to my tiny board, but it's the best I have and what we have to deal with. So 3 times 3 is 9 cubed root of 20. Now, is there a perfect cube less than 20 that's a factor of 20? The only options I would have, guys, and obviously greater than 1, otherwise you're just spinning your wheels. 8 is going to be my only option because 2 cubed is 8. And then my next one up, 3 cubed is 27. So it can't be 3, it'd have to be 2. Is 8 a factor of 20? And the answer to that is no. And so if I broke it down into its prime numbers and seeing why I don't have triplets, that I can pull one of them as factors, that I can pull one of them to the outside, I would just have to multiply them all right back together and end up with 20 again. And so my answer right here is this. 9, I know I kind of cut it off a little bit, but 9 cubed root times the cubed root of 20. That's my simplified answer. Again, in a calculator, you can punch it in and you can get a decimal for that, but it's not going to be correct because that's not written in standard form. And the calculators you guys have are not going to do that in standard form for you. Okay, number 3, stay with me. You guys are doing well. I know it's not easy, okay? This isn't going to be an easy chapter, but you guys have such sharp minds. You killed factoring. You guys did great with it. And you're going to do great with this as well, a little bit of practice and work. Number 3, what is the square root of 32 x cubed y squared? Okay, what is the square root of 32 x cubed y squared? This one's kind of fun. All right, here's what we're going to do first. I want you to tell me, is there a factor of 32 that is a perfect square, since we're dealing with a square root? Is there a factor of 32 that's a perfect square? Yes, there is. And what's the largest one you can possibly do? There are actually technically 2 ways, but go largest first. 4 and 8, well, 4 is a perfect square, but go bigger. And the reason for that is go up to another perfect square, and that's 16. I would start there. Now you can do the 4 thing, which you'll end up doing twice. I encourage you to go larger first because it saves steps. This is the same thing as 16 times 2 times x squared times y squared. Let's put that all underneath the square root symbol. Now the reason we chose 16 and 2 is because that's a large perfect square, and I can just take the square root of 16 and move that to the outside of the square root symbol. What's the square root of 16? What times itself gets you to 16? 4. And so I'm going to have outside the square root symbol now the number 4 because the square root of 16 is 4. And then I'm going to rewrite square root 2 times x cubed times y squared. Now here's where things get kind of fun and interesting. I'm done with all that I can do with my numbers because 2's prime and that's not coming out. That's staying in there. But I'm going to write in what is understood and is not written as a number, that's the square root, right? And do you remember what you do with exponents if you're taking the square root of them? You divide them by whatever that exponent on the outside is. So in the case of x to the third, I would divide x to the third by x to the second. In the case of y squared, I would divide that 2 by the 2. Okay? So let's do that with each one. Whenever I do so, I have 4, right? I'm going to keep that on the outside. Okay, how many times evenly will 2 go into 3 when you divide it? Well, as far as a whole, only once. And therefore, I can pull out 1x to the outside because x squared divided by 2 is x to the first power, not under a square root symbol. And so I can pull that one of those x's to the outside, okay? But that's going to leave me with 1x under the square root symbol because I can't account for 1 that's underneath it. Does that make sense? I know that's kind of sticky right now. We're going to do a few of these, so stay with me. Okay? And the other thing is this. I have y squared, and I might even just write under here, I can get a whole x out here, but that's going to leave me with x to the first power under there, so I know to rewrite it under there. Now, y to the second power, if I divide that by 2, because when I take the square root, that's what I do with the exponents. Whatever exponent is out there gets divided into that exponent. Y squared divided by 2 is what? It is a single y to the first power, and it's even, and that's enough to get me to the outside. And so I have 4x out here, and now I have a y on the outside, and I have no y's left over underneath the square root symbol. And so what I rewrite under the square root symbol is that which I have left, the number 2, and x just to the first power. And I don't write the to the first power because it's just understood to be that way. So 4xy times the square root of 2x. I know this is a little confusing, guys. It's not easy. I get that. But let me add one nuance to it before we move on. I want you to look at this rule. If when you're taking the nth root of x to the nth power, listen to me. If both the root that you're taking, as well as, both of these have to be the case, as well as the exponent of which you're taking the square root, if both of those are even, meaning if, for instance, if you're doing the square root, well, a square is an even number, and if this is squared, or if this is to the 4th power, that's also even, and if that's the case, you put absolute value bars around that variable in your answer. Okay? Now I want you to look at what we had. This was a square root. That's even, right? But look, x to the 3rd power, that's not even. That's odd. And both of them have to be even to put absolute value bars around a variable. And so I'm not going to put absolute value bars around the x, but look at the y. It's a square root that's even. That y was originally squared. That's even, and since they're both even, I'm going to put absolute value bars around the y. Absolute value bars around that y. Now listen, if you forget to do that, I'm not going to be a real stickler about that because I know this is challenging enough. But that's the rule, and we need to incorporate it. Okay, it's probably as clear as mud right now. That's okay. I expect that. It's not easy. It's a brand new concept. But let's do it with another one and see if we're getting a little bit better at this. Okay, we're going to take the cubed root on number 4 of 16x squared, y to the 4th, z to the 6th. First thing I want to do number-wise is I want to break down 16 into 2 factors, one of which is a perfect cube. What is a factor of 16 that I know to be a perfect cube? I could do 4 times 4, but that's no good because neither one of those, and they're both the same number, 4 is not a perfect cube even though 4 is a perfect square. There's a difference. A perfect cube is a factor of 16 is the number 8 because the cube root of 8 we know is 2. 2 times 2 times 2 gets you to 8. And so I'm going to use 8. I'm also going to use the factor of what it takes from 8 to get me to 16, which is 2. Okay? And then we also have times x squared, y to the 4th, z to the 6th. Okay, let's simplify. We can pull the cubed root of 8 to the outside. What's the cubed root of 8? We already determined. What times itself gets you to 8? 2. And so I have 2 now on the outside of the cube root symbol. Okay? And I'm going to be left with, on the inside, number-wise, 2. I can't do anything more with it. That's prime. You can't break that down anymore. And so 2 times x squared times y to the 4th times z to the 6th. Now, what I got to do from that point is I have to take the cubed root of all these exponents, or all these variables with exponents. And the way I do that is divide 3 into 2, 4, and 6 for each respective variable. I'm going to rewrite 2, but I'm going to see what it is as a whole exponent that I can pull out from under that cube root symbol. Now, does 3 go evenly into 2? No. Therefore, I can't do anything with that x squared, because that cubed root is greater than the exponent of the variable. Can I do anything with y to the 4th? Well, will 3 go evenly into 4? Yes, it will one time. And so I can pull 3 of those y's, or y to the 3rd, because y to the 3rd, the cube root of it divided by 3 is 1. And so I can pull out one of those y's to the outside. But when 4 is divided by 3 and I get a whole 1, or y to the 1st, out of that, how many y's, or to what power, do I have left over underneath? I still have y to the 1st, because when you divide 3 into 4, even though you get a whole 1, there's going to be a remainder of 1. Okay? How about z to the 6th? When I divide that 3 into that exponent of 6, it goes into it how many times? Evenly, and it does so twice. So what's cool is, I get to pull z to the 6th power divided by 3, which is z squared. I get to pull that whole z squared to the outside of the cube root symbol, and I'm done with my z's. There are no z's that are left over. And so what I have remaining is this: 2yz squared times the cubed root of, remember, I could do nothing with my x squared, and so that remains underneath the cubed root. I had a y to the 1st that was left over, and so that stays underneath. And there's one thing that I missed. Did you guys notice as a number? I overlooked that, didn't I? Easy to make a mistake when you're dealing with so many individual terms, combining them together. 2, don't forget to write your number first. X squared is left over, I can do nothing with it. Y to the 1st is left over, I couldn't completely get rid of that underneath the cubed root, but I did get rid of the z to the 6th, because when divided by 3, I can move that to the outside, is z squared. So my answer is 2y z squared times the cubed root of 2x squared y. Wow, that's crazy stuff, isn't it? Guys, I'm going to tell you right now, listen to me. It's complicated. It's not easy, but it's not too hard. It's not something that your brilliant mind cannot absorb and cannot duplicate and cannot do on its own. I have every confidence that it can do so. But look, none of these are absolute valued outside of the cubed root, because if the n in either one of these scenarios is odd, and for every one of these it's odd because of the cubed root, you don't use absolute values. Alright? And I could explain all the mathematical process behind it, but it would just be too confusing, and honestly wouldn't be worth your time. So, alright, 5a. If I take the cubed root of x plus 2 in parentheses cubed, what do I have? These last two, let's end on an easy note. As complicated as they might appear, they are not at all. And here's the reason why. The cube and the cubed root, guys, nothing more than cancel each other out. Remember, a cubed root is the opposite or the inverse of a cube, and so they just cancel themselves out. And so what is the cubed root of, in parentheses, x plus 2 cubed? It's nothing more than x plus 2. That's it. Not too hard, is it? Alright, how about 5b as I gather my lid that I'm spilling on the floor? The square root of, in parentheses, x plus 2 squared. Well, understanding that the square root has a 2 in that v, what do you think happens to the square root and a square? They nothing more than just cancel each other out. And so what am I going to have as my answer? X plus 2 as well. That's not too hard, is it? Now, there is one caveat on this one. Be a little bit careful. Because remember, if you have the nth root being taken of a term, and it's to an nth power, and both of those terms are even, what do? That's even. What's the rule? What do I do if both of those terms, the root as well as the exponent of the term itself, are even? Then I have to put absolute values around everything that was found underneath the square root symbol. And that is all she wrote for simplifying radicals. Thank you. Right? Again, guys, I know this isn't an easy lesson. This is a tough one. I believe it's probably one of the most difficult, if not maybe even the most difficult. I don't know, chapter 3, remember all those word problems? Those are pretty tough, the inequality word problems. But it's one of them. It may very well be the toughest section that we've had in math so far. But I know you guys can do this with some work. I know you're not going to have it. I don't have it. Nobody has it, just like that, or didn't have it. It takes some practice, and it's going to take some time. And with it, you guys are going to do really well with it. And you're going to finish up this chapter strongly, I have no doubt. All right, that's all for math, guys. Appreciate your time.